Okay, welcome back. You see, when it comes to RC and RL circuits, we tend to take a few things for granted. One of them is what the fact that in a source free RC or RL circuit, eventually, that is at a steady state, all the capacitors and inductors will get fully discharged so that at steady state, all voltages and currents are going to be 0. And this is true in general for any source free circuit. Okay, I'll just write that down. What is it? In a source free, it could be RC circuit, it could be an RL circuit. Usually what happens, the capacitor and the inductor will get fully discharged through the resistors in the network so that at steady state all voltages and currents are going to be 0. Okay, all voltages and currents are what? 0 at steady state, and this is true in general. Okay, and then the other trivial fact that we have is what? For a capacitor, the voltage drop cannot change instantaneously, and for an inductor, the current flowing through it also cannot change instantaneously. Okay, and for the very reason, when we draw the circuit at t equal to what? 0 minus. Okay, so whenever the switching action takes place at t equal to 0, we always draw the circuit at t equal to 0 minus. Okay, so when we draw the circuit at t equal to 0 minus, we do not find each and every voltage and current in the circuit. We only find the voltage drop across the capacitor and the current through the inductor. Okay, so at 0 minus, we only find Vc and IL. Of course, the assumption is what? That the circuit starts at t equal to minus infinity, so that at t equal to 0 minus, it reaches what? Steady state. And if it is a DC steady state, capacitor can be assumed to be an open circuit, and the inductor will behave like a short circuit and so on. Okay, so my point is what? When you draw the circuit at t equal to 0 minus, we only find Vc and IL, but we do not find the voltage drop across some resistor in the network, because the voltage drop across a resistor, it can change from 0 minus to 0 plus, whereas Vc and IL do not change from t equal to 0 minus to t equal to 0 plus. Okay, once you draw the circuit at t equal to 0 minus and find Vc and IL, what next? Remember, the final expression is what? Final plus initial minus final into e power minus t by tau. So for that, you need to find the initial value of the particular voltage or current for which you are trying to write down the expression as a function of time. Okay, and initial value is what? The value of that particular current or voltage at 0 plus. Okay, so after you draw the circuit at t equal to 0 minus, then we usually draw the circuit at t equal to 0 plus to find the initial value. And when we draw the circuit at t equal to 0 plus, Vc and IL will be same as what they were at t equal to 0 minus. Okay, that is the reason why we find only Vc and IL at 0 minus, so that these two can be used when we draw the circuit at t equal to 0 plus to find the initial values of different currents and voltages. Okay, so these are two simple facts that are taken to be obeyed by RC and RL circuits. The first one is what? In a source free circuit, all voltages and currents will eventually decay to what? 0. And the second one is what? Voltage drop across the capacitor and the current through the inductor will be same at both 0 minus as well as 0 plus. So in this session, we shall look at a few interesting cases where these facts are not obeyed. So these are some kind of special cases where a few things will happen which are contrary to what our common belief tells us. Okay, so let us start with something very simple. Let's say we have a simple RC circuit. RC, and let the input applied to this RC circuit be a step voltage. Let that be 10 times U of t. 10 times U of t. Now, how will this circuit respond? Let's say Vc is the variable of interest, which is the voltage drop across the capacitor. Okay. Now, at t equal to 0 minus, by the way, let us denote this by Vn. Okay. So, what is Vn? It is 10 times U of t. At t equal to 0 minus, the value of Vn, is it not 0? Yes. So, what is the circuit going to be? Is it not this thing, RC? Because Vn is what, 0. In place of the voltage source, I have drawn a short circuit. I hope you agree with that. Okay. Now, because it's a source-free circuit, obviously Vc is going to be 0. Okay. So at 0 minus, what is the value of Vc? It is 0. Now, let us also draw the circuit at t equal to 0 plus. Just after t equal to 0, what is the value of Vn going to be? Will it not be 10 volts? Yes. So in place of Vn, I have drawn a 10 volt source, and then we have the RC circuit. Okay. And this is what Vc. Just tell me, what is the value of Vc going to be at 0 plus? Will it not be same as Vc at 0 minus, which is 0? So at 0 plus as well, Vc is going to be 0. So that what is the current flowing through R? Is it not 10 minus 0 by R, which is 10 by R? And this 10 by R will flow through the capacitor, and that will start charging the capacitor. And when the capacitor starts getting charged, Vc will definitely start increasing, because current, you can say, is flowing from plus to minus. Vc will start increasing. But then, as Vc increases, the current through R will decrease. So the rate at which the capacitor is going to get charged, it keeps on decreasing. So initially the rate at which it gets charged is what? 10 by RC. Then it keeps on decreasing. Eventually, the cap will get charged to what? 10 volts, right? Because at steady state, C will become open. So this 10 volts will appear across this open circuit. So what is Vc at infinity? It is 10 volts. And this is what? The final value of Vc. And what is Vc at 0 plus? It is 0. So what is the 0 volts? It is the initial value of Vc. And of course, tau is what? RC. Once you know final and initial values of Vc, you can just like that write down the expression for Vc of t for t greater than 0. Okay. So what is Vc of t? Final plus initial minus final into e power minus t by tau. So in place of final, you write down 10. In place of initial, you write down 0. You will get 10 times 1 minus e power minus t by RC. This is quite a familiar thing. Okay. Let me also draw the waveform for Vc. Vc plotted versus time. Okay. Look at this. Vc is what? T. Let this be 10 volts. So what is the value of Vc for t less than 0? It is 0. Okay. So up to t equal to 0, the value of Vc is what? 0. Yes. And what happens to the value of Vc after t equal to 0? After t equal to 0, the cap will start getting charged, and exponentially it will get charged to what? The final value, which is 10 volts. You know, it does something of this sort. Okay. That's all. This is how Vc changes after t equal to 0. So up to t equal to 0, Vc is what? 0. And after t equal to 0, Vc will exponentially rise to 10 volts from 0 volts. Okay. Okay, now also we have the same circuit, 10 times U of t applied across this RC circuit. This time I am calling this C as what? C1. And the drop across C1 is what? Vc1. Okay. Now let me add a capacitor, across the resistor. Let me call the capacitor as what? C2. Okay. Okay, question number 1. Now what is the number of capacitors in the circuit? clearly there are two capacitors. So is it going to be a first order circuit or a second order circuit? In fact, how do you determine if it's a first order circuit or a second order circuit? You have to make the sources 0. Then you try to simplify the circuit as much as you can. Then in the simplified circuit, you count the number of energy storage elements. That will be the order of the circuit. So here also, if you make the input source 0, input source is what? Voltage source. So when you make this voltage source 0, it becomes what? A short circuit. When this becomes a short circuit, you will find that C2 or C1, all three will be in parallel. Now because C2 and C1 are going to be in parallel, both of them can be clubbed into a single capacitor whose value of capacitance is what? C1 plus C2. So for this circuit, what is the equivalent capacitance in the simplified network? It is C1 plus C2. I hope you have followed this, okay? First, you make the input source 0. Then in the simplified circuit, C1 and C2 will appear in parallel, which can be clubbed into a single capacitance of value C1 plus C2. And of course, because there is only one resistance, the equivalent resistance is going to be simply R. So now what is the time constant of this first order circuit? Is it not R equivalent times C equivalent, which is R times C1 plus C2. R times C1 plus C2, okay? Now let's find out how VC1 is going to vary with time. And let me call this voltage drop as what? VC2. Because after all, R and C2 are in parallel. Always they are going to have the same voltage drop. So this one is what? VC2. This one is what? VC1. And this is what they applied voltage, which is 10 times U of t, okay? Once again, as we always do, let me draw the circuit at t equal to 0 minus, okay? Look at this. At t equal to 0 minus. Just before t equal to 0, the value of unit step function is what? 0. So 10 times u of t is also what? 0, okay? So in place of the source, I put a short circuit and then R, this one, sorry, it is what? C2, and then this one is what? C1. Once again, you can see that R, C2 and C1 all three are in parallel, but then it's a source-free circuit. So obviously the voltage drop across C1 and C2 are going to be 0. So t equal to 0 minus, what is VC1? It is 0. What is VC2 as well? It is 0, okay? Clear up to this point? VC1 and VC2 at 0 minus both are 0, okay? Now, let me draw the circuit at t equal to 0 plus, at t equal to 0 plus. First of all, at t equal to 0 plus, what is the value of the input source? 10 times u of t just after t equal to 0. That is at t equal to 0 plus. Will it not be 10 volts? Yes. First, let me draw this 10 volt source. And then R, across which we have C2. And then this thing which is what? C1, okay? And what is this voltage drop? It is VC2. What is this voltage drop? It is VC1. Now, usually what we tend to do is what? The value of VC1 and VC2, because both are voltage drops across capacitors, they will be same at 0 minus as well as 0 plus. So if we try to do the same thing, which is what? VC1 equal to VC2 equal to 0. And by the way, I am not having a loop here. Now for this loop, we can always write KVL. Of course, KVL will have to be satisfied. Now when you write KVL around the loop, you will get what? This voltage drop plus this voltage drop equal to what? This voltage drop. Is it not this thing? I mean the KVL equation, VC2 plus VC1 equal to what? 10 volts. But if you take VC1 and VC2 to be 0, why? Because at 0 minus both were 0. So at 0 plus also, usually they will be 0. And here if you take both of these to be 0, Then look at this equation, KVL equation. Is it not 0 plus 0 equal to 10 volts? 0 plus 0, is it really 10? No, right? So clearly, what is getting violated? KVL is getting violated, okay? Which means at 0 plus VC1 and VC2 cannot be 0. So VC1 and VC2 have to be some non-zero values so that VC1 plus VC2 will be equal to what? 10 volts. So if VC1 and VC2 have to be some non-zero values, does it not mean the value of VC1 and VC2 is different at 0 minus and 0 plus? Which means what? The voltage drop is changing instantaneously. Different at 0 minus and 0 plus, it means what? Voltage drop across the cap, it is changing instantaneously. And in this circuit, that will happen, okay? Let me just play this off, okay? You see, during the time of switching, that is at t equal to 0, what is happening to the value of input? Is it not changing from 0 to 10? Because just before t equal to 0, the value of input is what? 0. And just after t equal to 0, the value of input is what? 10. Just before 0, it is what? 0. Just after t equal to 0, it is what? 10. So clearly at t equal to 0, input is suddenly changing from 0 to 10 volts. And that is what is the meaning of 10 times u of t, okay? So at t equal to 0, when its value is suddenly going from 0 volts to 10 volts, 0 volts to 10 volts. And before t equal to 0, both the caps, can I say, they are uncharged. VC1 is what? 0, uncharged. VC2 is also what? 0, both are uncharged, okay? And at t equal to 0, input is what? Suddenly changing from 0 to 10 volts. You see, sudden change, is it like a low frequency signal or a high frequency signal? Sudden change is what? High frequency signal, okay? Sudden change, it is like a high frequency signal. Slow change is what? Low frequency. No change is what? DC. I'll just repeat it. Not changing is what? DC. Slowly changing is what? Low frequency. Rapidly changing is what? High frequency. Sudden change is what? It is almost like infinite frequency, okay? So if you look at the spectrum, during the instant of the sudden change, it is as if the frequency will tend to what? Infinity, okay? Anyway, you see, for a capacitor, you must be knowing that its impedance is what? 1 by j omega c, or the magnitude of the impedance is what? 1 by omega c. So Zc is what? Impedance of capacitor, which is 1 by j omega c. Mod Zc is what? The magnitude of the impedance, which is 1 by omega c. You all must be knowing this, okay? Now, at the time of switching, because the value of input suddenly changes from one value to another value, at that instant, it is as if a very high frequency signal is driving this RC circuit. A very high frequency signal is driving this RC circuit. When omega tends to what? Infinity, because it is like high frequency. When omega tends to infinity, what will mod Zc tend to? Does it not tend to 0? Yes or no? Omega tending to infinity, denominator tending to infinity, overall fraction will tend to what? 0. So at the time of switching, when you have a sudden change in the value of input, at that instant, the capacitor will behave like a 0 impedance. What is a 0 impedance? Is it not like a short circuit? Yes. So at the time of switching, capacitor will have a very, very small impedance. It is almost like a short circuit. Now look at this resistor. Is it not across C2? Look at R. It is across C2. Now R at the time of switching, that is between 0 minus and 0 plus, is it not across a very small impedance? Any resistor across a very small impedance, is it not simply the very small impedance? Yes or no? Large resistance in parallel with very small resistance. The equivalent is what? That very small resistance. In the same way, R in parallel with a very, very small impedance, it is as if you have the very small impedance. So during the time of switching, because C2 will have a very small impedance, R can be neglected? Yes or no? Because all the current will only prefer that path which has got very, very small impedance. So no current will flow through R. No current flowing through R, it means what? R can be removed or ignored or neglected or treated as an open circuit. Okay. So at the time of switching, R can be neglected since it is in parallel with C2, which is going to have a very, very small impedance. Okay. So just look here. Because R can be neglected, I'll just remove R. So this is my circuit at t equal to 0 plus, where R has been removed or assumed to be an open circuit. Now look at this. Across this voltage source, are we not having two capacitors? And what is happening to the voltage source? It is changing from 0 to 10 volts. So when the value of the input source changes from 0 to 10, and then across this voltage source, you have two capacitors in series. This change, should it not be distributed between the two capacitors? And that is what is capacitive voltage division. Okay. So delta V in is what? The change in input voltage. And since across this input source, we have two capacitors in series, even this delta V in is supposed to be divided or distributed between C1 and C2. And what is that capacitive voltage division? The drop across C1 will be proportional to what? C2. And similarly, the drop across C2 will be proportional to what? C1. Okay. So what is the change in voltage drop across C2? Delta V in into C1 by C1 plus C2. Okay. Delta V in into C1 by C1 plus C2. That is what? The change in voltage drop across C2. So if I ask you, what is the actual voltage at t equal to 0 plus, will it not be the voltage drop across C2 at 0 minus plus the change in voltage across C2 at the time of switching? Initially, that is what, before t equal to 0 or at t equal to 0 minus, both VC1 and VC2 are 0. So from 0, if it changes by this much, the value of the voltage drop across C2 at 0 plus is also what? The same thing. That is what? Delta V in into C1 by C1 plus C2. And here, as an example, let me take both the capacitors to be identical. In other words, they'll have the same value of capacitance. Okay, so C1 equal to C2 equal to what? C. So what is delta V in? 0 to 10. So delta V in is what? 10 volts. If C1, C2 both are equal to C, then is it not 10 into C by C plus C, or 10 by 2, which is 5 volts? Yes, that's all. This is what? 5 volts. In the same way, even VC1, you can say it is what? 5 volts. So that 10 equal to what? 5 plus 5. So what is the value of VC1 at 0 plus? It is not 0. It is what? 5 volts. And what is the value of VC2 at 0 plus? It is also not 0. It is 5 volts. I hope my argument is clear. Two important points. Okay. At the time of switching, because the input suddenly goes from one value to another value, it is like having a very high frequency signal driving this RC circuit, and at very high frequency, the capacitor is going to have a very small impedance. Since you have this R across a very small impedance, R can be neglected, then it is as if you have two capacitors in series across this input source, so that the change in input will get divided between the two capacitors. Okay, and that change will get added to the corresponding voltage at 0 minus. In this case, at 0 minus both are 0. So the value of voltage drop across C2 at 0 plus is what? 5 volts. And the value of the voltage drop across C1 at 0 plus is what? Again 5 volts. Of course, C1, C2 both are equal to what? Some C. Okay. So what is this 5 volts? Is it not the initial value of VC2? And what is this 5 volts? Is it not the initial value of VC1? That's all. Now we have found initial values of VC1 and VC2, and they are different from the corresponding values at 0 minus. Okay. And what next? We must find the final values of VC1 and VC2. And for that, let me just draw the circuit for t greater than 0. See, for t greater than 0, 10 times E of t is what? Again 10 volts. 10 volts. Then you got R. Then this one is what? C2. And this one is what? C1. Again, when this circuit reaches DC steady state, at what point in time? At t equal to infinity. And by the way, what steady state is it? Is it not DC steady state? Because for t greater than 0, the value of input does not change. It will always be equal to what? 10 volts. It is as if a DC voltage is applied to this RC network. Okay. So at DC steady state, capacitors will behave like open circuits. I'll just replace C1 and C2 with open circuits. Look at this. So C1 replaced with open circuit. C2 also replaced with open circuit. Okay. So this one is what? C2, and this drop is what? VC2. And this one is what? C1. And this drop is what? VC1. So first of all, what is this current? Open circuit current is what? 0. What is this current? Again, open circuit current is what? 0. Because these two currents are 0, even the current through R is what? 0. Current through R 0, it means what? Drop across R is also 0. So does it not mean VC2 at t equal to infinity R steady state, it is what? 0. Yes. And then because this drop is what? 0, this entire 10 volts, should it not drop across this open circuit as what? VC1. So what is the value of VC1 at steady state? It is 10 volts. That's all. So VC1 at infinity is what? 10. Whereas VC2 at infinity is what? 0. Okay. So VC1 at infinity is what? 10 volts. VC2 at infinity is what? 0 volts. Now for both VC1 and VC2, we know the initial and final values. Okay. For VC1, initial value is what? 5. Final value is what? 10. And for VC2, initial value is what? 5. Whereas the final value is what? 0. Once you find initial and final values for both VC1 and VC2, we can write down the expressions for VC1 and VC2 for t greater than 0. And here what is tau? R times C1 plus C2. Since C1 and C2 both are assumed to be equal to what? C. Is it not 2 RC? C1 is what? C. C2 is also what? C. 2C times R is what? 2 RC. That's all. Tau is what? 2 RC. Initial, final. Let us write down VC1 of t and VC2 of t for t greater than 0. Okay. Whether it is VC1 or VC2, both are going to be the same form. Final plus initial minus final into e power minus t by tau. Okay. So VC1 of t, final is what? 10 plus initial is what? 5. Again minus final, which is 10 e power minus t by 2 RC. And that is what? 10 minus 5 e power minus t by 2 RC. Then what about VC2 of t? For VC2, initial value is what? 5. Final value is what? 0. Okay. So final plus initial. Final is what? 0. Initial is what? 5. So is it not 5 times e power minus t by 2 RC? And of course, this is for t greater than 0. This is also for t greater than 0. Understood? Let me also plot both VC1 and VC2 versus time. Okay. Look at this. See, VC1 up to t equal to 0. Up to t equal to 0. What is VC1? It is 0. Okay. So up to t equal to 0, VC1 is what? 0. Like this. And what is happening to the value of VC1 at t equal to 0? Just before t equal to 0, it is what? 0. And just after t equal to 0, it is what? Not 0, it is 5 volts. Is it not suddenly changing from 0 to 5 volts? Yes. So at t equal to 0, the value of VC1, it suddenly changes from 0 to 5 volts. And what is the final or the steady state value of VC1? It is 10 volts. VC1 of infinity is what? 10 volts. And how is it going from 5 to 10? It is exponentially going from 5 to 10. Okay. That's all. This is the complete plot between VC1 and time, okay? VC1 versus t. So up to t equal to 0, VC1 is what? 0. At t equal to 0, VC1 suddenly changes from 0 to 5 volts. Then for t greater than 0, VC1 will gradually increase from 5 to 10 volts, okay? Now if you try to draw a similar plot for VC2, if you try to draw a similar plot for VC2, even the value of VC2 up to t equal to 0 is what? 0, yes? So up to t equal to 0, VC2 is also what? 0. And what is the value of VC2 at 0 plus? It is again 5 volts, which means at t equal to 0, even the value of VC2 suddenly changes from 0 to 5 volts, just like VC1. Just like VC1. VC2 also suddenly goes from 0 to 5 volts at t equal to 0. And what is the final or steady state value of VC2? It is 0. Okay, VC2 of infinity is what? 0, which means for t greater than 0, it will exponentially decay what? 0 from 5 volts. Okay, so it does something like this. So red color plot is for VC2, whereas the yellow color plot is for VC1. So what is the important point here? At t equal to 0, both VC1 and VC2 are suddenly changing from one value to another value. In this case, they are suddenly changing from 0 to 5 volts. Okay, so there is one exceptional case where the voltage drop across the gap is able to suddenly change from one value to another value. Okay, and when is it happening? It is happening at t equal to 0. So at t equal to 0, there will be an impulse current flowing in the system, due to which there will be instantaneous charge transfer from the voltage source to both the capacitors, and that is the reason why we have the sudden change in voltage from 0 to 5 volts for both the capacitors. Okay, this time let us look at a source-free RC circuit, which is something like this. Let's say we have one capacitor C1 across which the voltage drop is what? VC1, and then you have this switch which is being closed at t equal to 0, and on the right side of the switch you have another capacitor before which you have this resistor. Let the other capacitor be C2, and VC2 is what? The voltage drop across capacitor C2. And let us say VC1 at 0 minus, that is what? The initial value of VC1, let it be some 10 volts, okay? And let's say the capacitor C2 is what? Initially uncharged, which means VC2 at 0 minus is what? 0. You understood? Yes. And again, for the sake of simplicity, let us assume C1 and C2 both are equal. They need not be equal. Okay. So as an example, let us take them to be identical. Let them be equal to what? C and so on. Okay. So VC1 of 0 minus is what? 10 volts, which means C1 is what? Initially charged, whereas VC2 at 0 minus is what? 0. So C2 is what? Initially uncharged. And then you have this switch which is being closed at t equal to 0. Okay. So what will happen in this circuit after you close the switch at t equal to 0? Okay. For that, let me just draw the circuit at t equal to 0 plus. First of all, at t equal to 0 plus, the switch is what? Closed. And then you have this resistor R, capacitor C2, capacitor C1. You see, from 0 minus to 0 plus, obviously the voltage drop across C1 is not going to change. It will remain at its initial value of 10 volts, and same is the case for C2 also. Okay. So for C2 also, the value of VC2 at 0 plus will be same as what? VC2 at 0 minus, and that is what? 0 volts. So what is the voltage at this point? It is 10 volts. What is the voltage at this point? It is 0 volts. So what is the direction of current through the resistor? Does it not flow from left to right? That is what in this direction, high potential to low potential. And what is the value of this current? Like initially it will be what, 10 by R. Now look at this current 10 by R. Through C1, is it not flowing in the upward direction? And look at this upward direction. Is it not flowing from minus to plus? I told you what, through any capacitor, if the current is flowing from minus to plus, it is as if the cap is what, getting discharged. In other words, the value of the voltage drop, it will decrease, okay? So what is happening to VC1? It is reducing with time because the current is flowing from minus to plus. What about the other capacitor C2? Look at the same current flowing through resistor. Through C2, does it not flow from plus to minus? Again, for a capacitor, if the current is flowing from plus to minus, it means what? The cap is kind of getting charged, in which case the voltage drop will increase with time. So VC1 is what? Decreasing, whereas VC2 is what? Increasing with time. And what is the initial value of VC1? It is 10. And what is the initial value of VC2? It is 0. Just for the sake of completeness, let me write down VC1 at 0 plus to be equal to what? 10 volts. And VC2 at 0 plus to be 0 volts. Okay. So what is happening here? Whatever initial charge is stored on C1, that is being transferred to what? C2 through this resistor R, so that VC1 is what? Decreasing with time, and VC2 is what? Increasing with time. Now the question is what? Does the capacitor C1 fully get discharged because it's a source-free circuit? See, when does the capacitor stop getting charged or discharged? When the current through it becomes 0. And the current flowing through both C1 and C2 is what? The current flowing through the resistor. So whatever current flows through R, the same current will charge what? C2, and the same current will discharge C1. And this discharging current or this charging current will become 0 when the current through R becomes 0. When does the current through R become 0? When the voltage drop across R becomes 0. And when does the voltage drop across R become 0? Is it not when this voltage and this voltage become equal? In other words, current through R becomes 0 when both C1 and C2 are at the same voltage. In other words, VC1 should be equal to what? VC2. It is possible, right? Because VC1 initial is what? 10 volts. Let this be 10 volts. VC2 initial is what? 0. And what is happening to VC1? It is continuously falling. And what is happening to VC2? It is what? Continuously increasing. So VC1 starts at 10 volts. VC2 starts at 0. VC1 is what? Decreasing. VC2 is what? Increasing. One is decreasing, the other one is what? Increasing. At some point, both will become equal. Yes or no? One is falling, the other one is what? Increasing. At some point in time, both will become equal. And when both become equal, that is when VC1 becomes equal to what? VC2, the current through R becomes 0. When the current through R is 0, even this charging current and this discharging current, both will become 0. And that is when the circuit reaches steady state. You understood? So at steady state, it is only the current through R that becomes 0. And when does the current through R become 0? When VC1 becomes equal to what? VC2. Because VC1 is what? Decreasing. VC2 is what? Increasing. At some point, VC1 becomes equal to what? VC2. Now the question is what? What is that common voltage that both VC1 and VC2 will reach and become equal? You understood? Yes. I'll just draw a closed volume. Just pay attention. Please look at this closed volume shown in yellow color. What is inside this closed volume? I am not having the upper plate of C1, the upper plate of C2, and also this resistor and the switch, which is being closed at t equal to 0. Now, what is in between the two plates? You have a dielectric, which is an insulator through which no conduction current can flow. So there is no physical charge transfer through any dielectric. Okay. Now, if you look at this closed volume, how is it separated from the outer or the external world? Is it not separated through, this dielectric and also this dielectric, through which I just said what? charge transfer cannot take place because this closed volume is separated by two dielectrics from the external world through which charge transfer cannot take place. Can I not say that the net charge within this closed volume is always going to be same because there is no charge transfer into and out of this closed volume. Always the net charge inside this closed volume is going to be same. Okay, so for this closed volume, the net charge is always going to be constant because it is separated from the external world through two dielectrics which are like perfect insulators, and through an insulator no charge will be able to flow and so on. So no charge flowing into or out of this closed volume. So within the closed volume, the net charge is always going to be 0. But there can be charge transfer within this closed volume, but the net charge is always going to be constant. Okay. Now, what is the net charge within this closed volume before closing the switch? Before closing the switch, C1 is what? Charged. C2 is what? Uncharged. If C2 is uncharged, what is the charge stored in C2? It is 0. So if you take top plate and the bottom plate, on both the plates, the charge is what? 0. But if you take C1, which is initially charged to what? 10 volts, what is the charge stored in C1? Q equal to what? CV. Yes, Q equal to what? CV. And we are assuming C1 and C2 to be equal to what? C. And what is the value? The voltage drop across C1, it is 10 volts. Is it not? 10C. Yes, 10C coulombs of charge stored in C1. It means what? On the positive plate, you have a charge of what? Plus 10C. And on the bottom plate, which is what? The negative plate, you have a charge of minus 10C. But then, it is only the top plate which is inside this closed volume. So if I ask you, what is the charge within this closed volume? Is it not the charge stored on the top plate of C1 plus the charge stored on the top plate of C2? And C2 is what? Initially uncharged. Charge stored on the top plate of C2 is what? 0. Whereas the charge stored on the top plate of C1 is what? 10C. So what is the net charge within this closed volume? It is also 10C. Now coming back to this case where eventually Vc1 and Vc2 will become equal. Vc1 decreasing, Vc2 increasing. At some point, Vc1 and Vc2 will become equal. Okay, and that is when the current flowing through R becomes 0. Once the current flowing through R becomes 0, even the values of Vc1 and Vc2 will not change anymore, because for the voltage drop across a capacitor to change, current must flow through it. But when the current through R becomes 0, no current will flow through either of the two capacitors, in which case both the voltages will become constant or they do not change with time. Okay, so let us say Vc1 at infinity, Vc2 at infinity is equal to some Vc, is equal to some Vc. Okay, now once again let me take the same closed volume. What is the net charge within the same closed volume at infinity? Now for C1 the voltage drop is what? Vc. For C2 also the voltage drop is what? Vc. What is the charge stored on the top plate of C1? Is it not Vc into C? And what is the charge stored on the top plate of C2? Is it not Vc into C again? So is it not Vc into C plus Vc into C, which is 2 Vc into C? Yes. So 2 Vc into C is equal to what? The initial net charge within this closed volume, which is 10 times C. Now C and C will cancel out. So that the value of Vc is what? 5 volts. Vc is what? 5 volts. What it means is both the capacitors will reach a common voltage of what? 5 volts. And that is where the circuit reaches steady state. Okay. So what is Vc1 of infinity and Vc2 of infinity? Both are equal to what? 5 volts. That's all. So Vc1 of 0 plus is what? 10. Vc1 of infinity is what? 5. Whereas Vc2 of 0 plus is what? 0. And Vc2 of infinity is what? 5 volts. Okay. And what is the time constant of this circuit? Since in the circuit for t greater than 0, C1 and C2 are in series. They can be clubbed into a single capacitor value C1 C2 by C1 plus C2, and of course there's only one resistor. So R equivalent is what? R, and C equivalent is what? C1 C2 by C1 plus C2. So tau is what? R times C1 C2 by C1 plus C2. This is the expression for tau. Okay. Now very quickly I'll just write down the expression for Vc1 of t. So what is happening to C1? Initially C1 is what? It is at 10 volts, and then through R it will get discharged. In other words, charge is getting transferred from C1 to C2, but the net charge within this closed volume will not really change. Okay. And from 10 volts it will drop to what? 5 volts. And for C2, which is what initially uncharged, the value of the voltage drop will go from 0 to again 5 volts. Okay, so Vc1 changing from 10 to 5, whereas Vc2 changing from 0 to 5. Okay, so for Vc1 of t, what is final? It is 5. What is initial? It is 10. Final plus initial minus final. Final is what? 5. Initial is what? 10. Again minus final minus 5. E bar minus t by tau. In the same way, what is Vc2 of t? For Vc2, initial is what? 0, final is what? 5. Initial 0, final 5. It means what? 5 into 1 minus t by tau. That's all. Of course, both are valid for t greater than 0. Okay. Understood, right? Yes. So what is the conclusion here? This is also what a source-free RC circuit. Usually in a source-free RC circuit, capacitors will get fully discharged, so that at steady state, the value of Vc is going to be 0. But here at steady state, what is the value of Vc1 and also what is the value of Vc2? It is not 0, it is some 5 volts. So it is possible that even at steady state, the voltage drop across the cap is not 0 in case of a source-free circuit. Okay. See, what is definitely going to be 0 at steady state? It is the current through the capacitor that is definitely going to be 0 at DC steady state. Because if the current is not 0, then the voltage drop will change. And at DC steady state, the voltage and the current are not supposed to change. They can be non-zero, but they have got to be constant. Okay. So at DC steady state, definitely the current through capacitor is going to be 0, irrespective of whether it's a source-free circuit or a circuit being driven by a DC source. Okay. So let me just quickly summarize the earlier example. We had one capacitor C, which is initially charged to what? 10 volts. And then you had this switch, which is being closed at t equal to what? 0. And then you had this resistor R. And you had one more capacitor C, which is initially, uncharged. And then let the voltage drop across the first cap be some Vc1. Let the voltage drop across the second cap be some Vc2. Let me just quickly plot Vc1 versus t. Here's what Vc1. This is what t. Okay. So before t equal to 0, Vc1 is what? 10. And after t equal to 0, what is Vc1 doing? Is it not going from 10 volts to 5 volts? Yes. Vc1, it changes from 10 volts to 5 volts. Whereas Vc2, that is what the voltage drop across the other cap, which is initially uncharged, will change from 0 volts to 5 volts. Okay. So Vc1 up to t equal to 0, it is what? 10. And after t equal to 0, it will exponentially decay to what? 5 volts. This is the plot for Vc1. In the same way, I'll also plot Vc2 versus time. Look at this. Again, Vc2 is what? The voltage drop across the other cap. Up to t equal to 0, it is what? 0. And then for t greater than 0, you can say it changes from 0 to 5. again in an exponential fashion like this. So these are the plots for Vc1 versus t and Vc2 versus t. If you want, you can also write down the expression for IR as a function of time. What is IR at 0 plus? You say at t equal to 0 plus, the voltage at this point, would it not be 10? And the voltage at this point, would it not be 0? So what is the current through R at 0 plus 10 minus 0 divided by R? You already know this, it is what, 10 by R. And what is the value of IR at infinity? At infinity, this becomes what, 5. This also reaches what, 5. 5 minus 5 drop is what, 0. Current is also 0. So for IR, that is the current through R, the initial value is what, 10 by R, and the final value is what, 0. Okay. So does it not exponentially decay from its initial value to the final value? Yes. So IR of t will also be of the same form, final plus initial minus final times e power minus t by tau. Final is what, 0. So it is what, 10 by R times e power minus t by tau. And tau, remember, is what, R times C1 C2 divided by C1 plus C2. Okay. Just for the sake of completeness, I'll also plot IR versus t. Again, up to t equal to 0, what is the value of IR? Because remember, for t less than 0, switch is what, open. If switch is open, it is what, an open circuit. No current will flow through what, an open circuit. Or the value of IR is also what, 0. So up to t equal to 0, the value of IR is what, 0. And what is IR at 0 plus? It is 10 by R, which means at t equal to 0, the value of IR will suddenly jump from 0 to what value? 10 by R, and then it will decay to what? 0. It will decay to 0. Understood? Yes. Okay, now an interesting thing to evaluate is what? What is the area under this, IR waveform that is under this curve? How can you find the area? Just integrate IR of t with respect to time from 0 to infinity. Yes, I'll just do that. So first of all, IR of t is equal to what? 10 by R times e power minus t by tau. So what is tau? R times C1 C2 divided by C1 plus C2. Since in this case C1 and C2 both are equal to C, C equivalent will be what? C by 2. So tau will be what? R times C by 2, or simply RC by 2. Yes. So tau is what? RC by 2. Okay. Anyway, 10 by R times e power minus t by tau, and this is for t greater than 0. Now to find this area, and by the way, what is this IR doing? Is it not transferring charge from C1 to C2? Yes or no? This current is transferring charge from C1 to C2. So when I integrate this IR from 0 to infinity, what is the value that I am going to get? Is it not the amount of charge transferred from C1 to C2? Let me call that as what? QT. So what is this Q sub T? It is the total charge that is transferred from C1 to C2. Okay, so QT, it denotes what? Charge transferred from C1 to C2. And what is QT given by? It is simply the integral of the current or the area under this current waveform. Okay, so integral IR dt from 0 to infinity. Already we know IR as a function of time. It is what? 10 by R times e power minus t by tau. So what is integral e power minus t by tau dt? I think it will be minus tau times e power minus t by tau. Okay, 10 by R times minus tau times e power minus t by tau, and then you have to plug in the limits. which are from 0 to infinity. Again, what is tau? It is RC by 2. So in place of tau, if you substitute RC by 2, R and R will cancel out. I think you'll get minus 5C. Minus 5C times the value of this integral. So in place of t, if you substitute what? Infinity. What is e power minus infinity? It is 0. What is e power 0? It is 1. 0 minus 1 is what? Minus 1. So the value of this thing is what? Minus 1. Minus 5c into minus 1 is what? Plus 5c. So what is the area under this current waveform? It is 5c. So the important point is what? That it is independent of R. So R can be any value. Always the charge transferred from C1 to C2 in this particular case is going to be 5C. Okay, it is what? 5C. In fact, without even integrating, we can say it is what? 5C. Because for both the capacitors, we know the initial and final values. Okay, for example, if you take C2 initial voltage is what? 0. So initial charge is also what? 0. And for C2, final voltage is what? 5 volts. Voltage 5 volts. Capacitance is what? C. So what is the final value of the charge stored on C2? Is it not C times 5 volts, which is 5C? Yes. And initial charge for C2 is what? 0. So what is change in charge for C2? 5C minus 0. I'll just write that down. So here Q is what? 5C. And here Q is what? 0. So what is the change in charge or delta Q? It is 5C minus 0. That is what? 5C. And that is the amount of charge transferred from C1 to C2, and this 5C is also what? The charge that is lost by C1. So initially the charge stored in C1 is what? 10 volts into C, which is 10C, and finally the charge stored is what? 5C. So from 10C it reduces to what? 5C. So the amount of charge lost by C1 is what? 5C, and that is the charge that has been transferred to what? C2. Okay. Anyway, the area under this is what? Always 5C, and that is independent of the value of R. Okay. Okay, now the question is, what happens when R tends to 0? So what do you mean by R tending to 0? This resistor, it becomes what? A short circuit. You see, when R tends to 0, look at this initial value of the current, that is what? 10 by R. R tending to 0, 10 by R, does it not tend to infinity? Yes or no? Does it not tend to infinity? And then what is the width of this curve on the right hand side? How long does it take for the circuit to reach steady state? Usually it takes what? 5 time constants. Let me call this as what? 5 tau. So 5 tau, and tau is what? RC by 2. And when R tends to 0, tau also tends to what? 0. Tau also tends to what? 0. If tau tends to 0, phi tau also will tend to what? 0. In other words, when R tends to 0, this initial value of IR will tend to what? Infinity, and the width of the curve will tend to what? 0. So does it not become a very, very narrow pulse kind of thing, where the height will tend to what? Infinity, and the width will tend to what? 0. Okay. Just for your convenience, I'll write it. So when R tends to 0, the waveform for IR tends to become a narrow pulse. And for this narrow pulse, the height, that is what? 10 by R, will tend to infinity. Height tending to infinity. And what about the width? Width is what? Usually phi tau. And when R tends to 0, tau will tend to what? 0. Phi tau also will tend to what? 0. So is it not like the width is tending to 0? Now what is this pulse whose height is what? Infinity, and width is what? 0. And the area is what? Finite. What is area? It is always going to be phi c, because area is what? Independent of R. So whether R is what? 0 or some non-zero value, always the area is always going to be 5c. So in the limiting case also, the area will remain the same and equal to what? 5c. So is it not an impulse? So when R tends to 0, IR will become an impulse current. Impulse current of how much area? 5c. So is it not simply 5c times del of t? This is how you get the popular circuit which you must have studied in your high school. where you have a switch. On either side of the switch, you have two capacitors, C1 and C2. And when the switch is what? Closed at t equal to 0, an impulse current will flow through the switch. That is how you get this impulse current. So in general, you have a resistor R, and this case is obtained when R will tend to 0, in which case you have this impulse current. Impulse current, it means what? There is going to be instantaneous charge transferred from one capacitor to the other capacitor, so that right after the switch is closed, both will reach a common voltage. It should be right, because after you close the switch, C1 and C2 will appear in parallel, and they should have the same voltage drop. And for that to take place, an impulse current will flow from one capacitor to the other capacitor, meaning an instantaneous charge transfer will take place. Okay. So how will these two waveforms get modified, Vc1 versus t and Vc2 versus t, when R tends to 0? Just now I told you what, when R tends to 0, an impulse current will flow. The voltage drop also will change instantaneously for both the capacitors. Okay, here it is taking some time to go from 10 volts to 5 volts, but when R will tend to 0, the change is going to be sudden or instantaneous. Okay, up to t equal to 0, it is what, 10. Suddenly at t equal to 0, when you close the switch, it will drop to 5. It just remains at 5. Similarly for Vc2 also, the change is not going to be gradual. It is rather going to be instantaneous. Okay, up to t equal to 0, Vc2 is what, 0. And suddenly at t equal to 0, it will jump to 5. It just remains at 5. So that you can see for t greater than 0, both are at 5 volts. Okay, it should be right because both are in parallel. Okay. Okay, in the same example, what is the energy stored in both the capacitors before the switch is closed at t equal to 0? Look at this. Before t equal to 0, what is the energy stored in both the capacitors? Before t equal to 0, Vc1 is what? 10. Vc2 is what? 0. So obviously no energy is stored in C2, and there is some energy stored in C1, and that will be at half C V square. Is it not half into C into the voltage squared, which is 10 squared, which is 50C? And then what is the energy stored in both the capacitors at steady state or at t equal to infinity? Yes. So after you close the switch and so on, it reaches what? Steady state, where both are at the same voltage, that is what? 5 volts. Okay, 5 volts across C1, 5 volts across C2. What is the energy stored in both C1 and C2? Half C V square. V is what? 5. So half into C into 5 squared is what? 25. Since you have two identical capacitors multiplied with 2, is it not 25C? So before you close the switch, the total energy stored in both the capacitors is what? 50C. And after you close the switch, and when the circuit reaches a steady state, the total energy stored in the capacitors is only 25C. So what is the energy loss in this particular event? Is it not 25C? Yes. So energy dissipated by the resistor, it is what? 25C. So what is being conserved? It is only the charge that is being conserved within that closed volume, but the energy is definitely going to get dissipated since you have a current flowing through the resistor. Even in the limiting case, when R will tend to what? 0, since you have an impulse current flowing, an impulse current is what? Like an infinite current. Infinite current flowing through an ideal switch, it will result in some non-zero power dissipation or energy dissipation. So even when R will tend to 0, you are going to have the same energy dissipation of what? 25C. And this is what? Irrespective of the value of R. Okay.